The steps for backpropagation go like this. We start with initial values for all the weights and biases in our network. If we're just starting out training from scratch, they could be initialized to random values. We feed our training data to our model and have our model produce outputs for each training example. This is also called the forward propagation or the feed-forward step. In theory, ideally we should be using all our training data in the single feed-forward step and running through all the outputs that our model will give for every data in our training set. But because training data could contain millions of examples and might be too much to process in one go, we might only take a chunk of the training data, and this is also known as batch learning. We calculate the cost. One common cost function would be to average over all the squared errors, which is the difference between our model's current output and what the output we want the model to have in order for it to predict the data. Then we use the chain rule to calculate the gradient, which tells us how to change each weight and bias in the neural network to cause our cost function to reduce. This gradient is calculated one layer at a time, starting with the output layer and then the highest hidden layer, and sequentially moving backwards through the hidden layers until we get to the first hidden layer. And this is where the term backpropagation comes from. Once we have the gradient with respect to all weights and biases, we update the values of all our weights and biases with the amounts defined by the negative gradient. And remember, some weights and biases will be updated larger amounts if it's going to cause a larger change to the cost function. And some weights and biases will be updated smaller amounts if changes to those cause smaller changes to the cost function. This is what the gradient tells us, is relatively how much to change each of the weights and biases in proportion to how much they're decreasing the cost function. After we update all the weights and biases, the cost function should reduce, and this is one step of learning. And we continue this process over and over again with our new current weights and biases and keep iterating until the cost function has reached a minimum. Now that we've talked about learning, I want to discuss the importance of having training data that's separate to testing data. So training data is the data that we've used for training the model, that the model was learning its parameters based on. But testing data is data that you could otherwise have used for training, but instead you reserve as a testing data set that you don't use during training. Because what we want is models that aren't just good at predicting the training data that it's already seen. We have models because we want models to be able to predict new data that it's never seen before. So we have a testing data set to evaluate how well our model is doing. A final thing I want to discuss about learning is the problem of overfitting, and why we always need to reserve part of our data to be used as a testing data set that is separate to our training data set. We often can train large, complicated neural networks to be extremely accurate at predicting its training data. But this doesn't mean that the model will be successful at predicting new data. Remember that the goal of our models is to make useful predictions about new data that it's not seen before. It's often the case that we can build models to be so specialized for accurate predictions on its training data that it starts getting worse at making predictions on new data. And this is known as overfitting. An intuition for an extreme example of a model that overfits would be a pure lookup table. Here, for every input, the model just memorizes the correct output, and this lookup table can achieve 100% accuracy at making predictions about data that it's already seen. But the lookup table has no capacity to generalize its knowledge and make successful predictions about new data. On this graph is shown an example of overfitting. The vertical axis is the error rate of the model, and the plot shows how the model's error rates change with increasing numbers of training cycles. The blue line represents the model's accuracy at predicting its training data, which is the data the model uses to learn its parameter values. We see that error rates on the training data continues to decrease with more training cycles. However, The red line shows the model's accuracy at predicting the test data, which is new data that the model was not trained on. Here we see that even though the error rates on training data decrease with the number of training cycles, as shown by the blue line, the red line shows that the error rates on the test data have started to rise. The model is getting less good at predicting new data, and we have the situation of overfitting. There are many techniques that computer scientists use to prevent overfitting, which include stopping the training early, and also a technique known as dropout, where we ignore random parts of our neural network when we're calculating the values for backpropagation.